These are the suggested problems. Hopefully, I will just try to solve one today and we can solve the other three tomorrow. Okay. So let's start with Newton's law of universal gravitation. Okay. Here's what it says. So, particle of mass m1 attracts another particle with mass m2, and if their distance is given by r, the strength of attraction is given by this equation. F is equal to some constant, first mass m1, second mass m2, divided by the square of the distance between these two masses, r squared. Okay? It's sometimes called inverse square law. Okay, it's like a very specific form. Here G is a constant. We call it the gravitational constant, and this can actually be determined experimentally. Like about 50 years after Newton published his law of universal gravitation, a guy named Cavendish came up with an experiment like this, which is now known as Cavendish experiment. Here you can see there's like a thin fiber connected to a rod, and there are two masses at the end of the rods. And there's like a mirror also attached to this fiber, and a laser beam can actually detect tiny movements of this beam, which is projected to a scale. Okay, a little bit of rotation of this rod can be detected, no matter how small it is. And you can bring up this probe mass to here, and you can look at the change in scale. And by this way, you can actually determine G to a very precise value. And here is its value. It's like 6.67 times 10 to the minus 11, and its unit is Newton meter squared per kilogram squared. So there are a couple of things to note about this law of gravitation. First of all, the Newton's laws of motion we introduced in the previous weeks, they describe the dynamics. So basically, under a given force, how does the particle move? Law of universal gravitation here introduces a particular force, and we call this force gravitational force. Okay. Now, since force is a vector quantity, we also need to take care of its direction. And for this, we can do some vector gymnastic, right? And we can actually express this gravitation in vector form. For this, for example, I can introduce just a little bit of bookkeeping. Suppose this is like origin, and your particle is M1, or like mass M1 is at R1. Your mass 2 is at R2. And I can calculate the distance between M1 and M2. If I want to know, for example, the distance from M1 to M2, this is basically R1 to like location of first particle with respect to second particle, and it's given by R1 minus R2. Or you can do it the opposite way. R21, location of second particle with respect to first particle, R2 minus R1. I hope you are familiar with this kind of index. And I think I try to advertise that this can actually help you in your calculations. And now, so these are all vector quantities, right? Once we introduce these, we can now write a vector expression for the gravitational force. So F, the vector F, force on one by the second particle is given by the same gravitational constant, product of masses, and the distance, like the position of one with respect to two. What is this? R1, 2, it's like this guy, position of one with respect to two. It's squared, and its direction is given by this unit vector along position of one with respect to two here, right? So the force on M1 is towards M2. You can also do the same thing for particle 2, right? Force onto by particle 1 is given by the same thing. And now this is position of 2 with respect to 1, which is R21. Now this guy, it's squared. There's like a square, and its direction is given by a unit vector along R21, which is this guy. So now, okay, just a small remark. Your book somehow uses a little bit different notation, but I think you can go ahead and check what I write here and what is written in your book. They agree, okay? You should go ahead and check maybe these index exercises. So these two forces, F12 and F21, actually form an action-reaction pair, okay? And you can actually check this just from these two quantities. And of course, you also need to use R12 is equal to minus R21, which you can see from this figure. So now, okay, we introduced the force between two masses, and previously we have been studying the gravity near Earth. Okay, now how do we connect these two things? We connect these two things this way. Previously, we called mg the force on a body on Earth, and g was like some gravitational acceleration. And now we know this force is actually given by this Newton's inverse square law, like g mass of the particle, mass of Earth, and radius squared, because the distance between the center of the Earth and the particle is to a good approximation r squared, assuming it's right on the surface. From this, okay, we can actually find what g we previously introduced is, right? It is equal to this gravitational constant, which is determined from Cavendish experiment, times mass of Earth and radius of Earth squared. If you remember, there was actually an estimation of radius of Earth in chapter 1. So maybe if you use this radius estimation and g from the experiment, and we know this one is 9.8, we can actually determine the mass of Earth. Do we accept Earth as homogeneous? Yes, for now we do, but I'll come to that. We'll talk about these technicalities in a little bit. Right now, I want you to think about this. Right now, I assume Earth is like perfect sphere, and the object is right on the surface. And suppose there's like a mountain like this, and this mountain has like an extra height, h, like this, and this mass is on top of this mountain. How much g differ in compared to the surface, right? I want to go through this exercise to understand this. So, and for this, let's estimate the gravity on Everest. So the height of Everest is like 8,850 meters above sea level. Based on this, what should the acceleration due to gravity be on top of the Mount Everest? Okay. Maybe I can give you just a couple of minutes. If you guys have any suggestions, I can also go ahead and start. What should I do? So mg, it's on Everest, should be equal to g m Earth divided by, exactly like you said, now this time r plus h squared. Okay, we can cancel these guys, and now g Everest is equal to g m divided by r plus h squared. Now we have all the numbers we need, so let's write this. Maybe I want to make it a little bit quicker, so h ever. Can you guys see what I write in this Python interpreter? Hopefully you can, right? Okay, so Everest is equal to 8850 meters height. of Everest. Okay. Now G Everest is equal to, we have G already introduced on top, M Earth we already introduced, divided by R Earth plus H Everest, and square of this should give me the, okay, this is gravity on Everest. Okay, and let's look what it is. Okay, this is 9.77. 9.77, and this should be meter per second square. Okay. Actually, this happens to be a, okay, maybe I can go back. This happens to be a reasonable approximation, and I actually copied this table from your book, which is, to me, interesting. Here are some differences in the gravitational constant by some different locations in the cities. In New York, elevation is 0, it's like 9.8. So is it in San Francisco, 9.8. In Denver, it's like a high place in the US. It goes to like 9.7, but it is not as small as Everest, right? Everest is obviously smaller. So this mountain is like higher than Denver. It's like Pikes Peak. I think it's like 2 hours from Denver. You can see it's like smaller from Denver, but it is still bigger than Everest, and so on. I actually looked at Ankara, Turkey. It also has a rather high elevation, and its gravitational acceleration seems to be 9.79. Now, okay, like one of you just mentioned, there is actually other things that comes into interplay when you are looking at the Earth's gravitational field. And here in this approximation, we neglected Earth's rotation. It actually plays a role, and we have an example for that. Another thing is Earth is not a perfect sphere, right? It is kind of compressed from the poles, and it is fat around the equator. So this kind of geometry also affects G. And finally, presence of like rocks and heavy materials in certain places, and like presence of light materials in other places actually also affect the value of G. Okay. Here is like a map I got from NASA. So this is the map of gravitational constants with high precision telescopes. And you can see that structure. It almost looks like a weather forecast, but it is not. It is, unfortunately, I couldn't find the color map, like color bars, but you can get the idea, right? For example, here, Himalayas are a little bit more apparent. You can see here, and for example, here, this is Marinara Trench, the deepest point on Earth. If you come down, this is the Pacific Ocean, right? And you can see this so-called ring of fire. It starts from like west coast of Chile all the way to North America, Pacific Northwest, and then goes through the pole, comes back through the Japan, and it's like kind of like a crazy pattern. And you can see it from the gravitational field, this structure. And here is Turkey. You can see it's kind of like mountainous region too. Okay. So another thing I said, it's the composition of Earth, right? So when you dig into Earth's crust, it actually has these layers of materials accumulates. And sometimes there are like these like layers of salt. Like there's like, I don't know, like a lake, some salt layer accumulates over like some geological time scale. There are other like layers accumulate on it with time. But the thing about salt, when you compress it like this, it behaves almost like a fluid, right? You just compress and it starts flowing like this. And as you compress and compress, it just bursts. When it bursts, it gives rise to this so-called salt domes, okay? and it just pierces through other layers like this. So what is interesting is when it pierces through other layers, it bends these layers like this. When it bends these layers, for example, this layer has oil in its composition, and when it is bent like this, since oil is light, it seems to accumulate here and here. And another thing is salt is generally lighter than other materials in the earth crust, at least here. And if you are the experimentalist walking here like this, with your ultra precise gravitational detector, when you come here, you detect a gravitational anomaly. And you say, hey, there must be like a salt dome here, which means maybe there's like oil here, and you can pipe in and find oil. Okay, this is what people use. So finally, let's think about Earth's rotation. And I want to talk about this because we have all the technical information to do this. Let's determine the gravitational acceleration on the North Pole and on the equator, right? Here is your example from your book, example 5. Assuming Earth is a perfect sphere, determine how the Earth's rotation affects value of g at the equator compared to its value at the poles. Okay. Centripetal force. Okay. So what about centripetal force? It won't affect g, I guess, but total pull will decrease. So I can write the free body diagram, right? There is like mg minus the normal force, but this should be equal to 0, but because there's nothing else. Then W is equal to mg, and g North Pole is equal to your weight there divided by m, which is equal to g itself. In poles, g is more. Let's see. Now, equator, okay, the same thing, mg minus, let's call this w prime because it's not the same, right? W prime should be equal to what? There is centripetal force. Good. Let's put the centripetal force down. It is m v squared over Earth radius. Okay. Now, then like w prime is equal to mg minus mv squared over r, or g equator is equal to w prime over m, which is equal to g minus v squared over r. Now, we need to determine v squared over r to see how much it changes, right? How do we determine v squared over r? Imagine you're here, you're standing, and Earth is spinning. That means you're spinning with the Earth. Like this. Right? How do I determine this v squared over r? 2 pi r over t. Okay, good. So v is equal to, okay, let's put 1 over r first. And we need to determine v. And v is 2 pi r, which is total path you take when you rotate around Earth like this. So 2 pi r, and total time, t. Right? And I need to square this whole thing. And this should be equal to 4 pi squared r, I just cancel r's, divided by t. Okay, let's call this delta G equator. Little bit of difference around the equator. Now, here in this expression, you know Earth radius. What about t? Do we know t? Oops, t squared, thank you. T squared, good job, thank you. Do we know t here? How do I get this number Yes, exactly, right? It's like 1 day because Earth is rotating by itself. Let's calculate this. T is equal to 24 hours times 1 hour is 60 minutes times 1 minute is 60 seconds, which is equal to like seconds 1 day. Okay. Now this delta G is equal to 4 times pi square divided by is T squared, right? Is that correct? 4 times pi squared times, oh, there's also an R times R. I think we put RE here. I think it should work. Oh, pi is what? Pi is 3.14159265, something like that. And this guy, okay, good. So what this means is like 3 parts in 1,000, right? Different. Just a tiny difference, but it is actually a non-negligible difference. This is, maybe I can write smaller g around equator. What did we assign W to? What did we assign? So here we didn't assign anything, right? So we are looking for W prime, and W prime is the normal force when you stand around equator. You're standing here, there is like some your weight. If you put a scale here, the scale will show W prime, right? And we put W prime to distinguish it from this W because we didn't know if they were equal. So here, this equation, there's like mg down, W prime up, and their difference on this side should be equal to m times a, right? It's Newton's law. But for circular motion, which is this, m times a is mv squared over r. And I solve this equation for W prime like this. And I defined G around equator must be W prime divided by M. And this was equal to G is like nominal value minus this V squared over R. So the conclusion is the difference of G around the equator is this centripetal acceleration V squared over R. And when we calculate this here, here, and here, we found it's like 3 parts in 100. Okay? Good. Thanks for the question. So let's continue. So I want to talk about a little about satellites and this so-called feeling of weightlessness or so-called apparent weightlessness, okay? And let's think about weight just a couple of minutes. So let's start with the simplest case. Imagine you're standing on the ground and I want to ask myself, what makes me feel that I have weight? What is it that we feel weighted, right? Definitely there is like a pull from the earth like this. And what does this do? It just, doesn't do anything. I'm standing on earth and I have a normal force, right? There is nothing else. So in this case, weight just gives rise to a normal force, which I probably feel on my legs if I stand for too long. That's what I mean by I feel weight, I guess, when I stand. So that's case number 1, okay? So the second case, so this is not the most general case, right? I could be moving, in particular, I could be falling with free fall like this. Suppose There's like an apple in a tree and it just falls. What makes us feel it is weighted, right? What we see here is gravity, or its weight is causing a motion with constant acceleration, g. And we know this example well too. We studied this. You guys are experts on this now. So are there any other cases? Yes. What could be happening is like this, right? Maybe I can clean this up just a little bit. And maybe I don't need that too. Suppose you are like some height above the earth. I don't know, let's call this h. And you move with a velocity v, and I still have mg. And I ask myself, what does this mg do in compared to others? So if v is small, I think it's not hard to say. Maybe it's going to be like, so gravity will pull this down, initial velocity will move this side, and it's going to be like this, right? Some kind of projectile motion. Actually, we studied this example too. You guys are also expert on this. Now here's the catch. What if I adjust this v such that this mg, which is the acceleration on this, is equal to mv squared over and total radius, like radius of Earth plus my height squared. What if I adjust v such that it satisfies this equation? What would I get? So that is one thing. This is like g effective, but we are right now interested in something else, right? We are now interested in, like, you are like above Earth some height, like say like really high, so that you are at atmospheric levels, maybe even beyond atmospheric levels, and you've moved with some velocity v, and there's always some mg or some mg effective, if you like. And I want to ask, what if I adjust this v and this mg effective such that, maybe I can write it like this. Like this, okay? What if I adjust v such that I have this? It's like weightlessness. What I understand from this is like you are going to have like a perfect circular motion around Earth, right? You will not fall on Earth. You will be in like a perfect circular orbit, and you will go round and round and round. You will never fall. Here, the key result is that mg causes some different results in compared to previous. It's not falling. It's not standing with some normal force, but it's like in circular motion. So the upshot is like, when I say I feel weightless, it actually is more about my psychology, right? The different scenarios can give rise to different things. But if this guy is like a satellite orbiting Earth, and you are standing on this satellite like this, you may look around and see, okay, here's Earth, and here's me, and I'm not falling. What's going on? I am actually floating in the air. But this is actually misleading because you are not floating in the air. You are circling Earth along with the satellites or along with your ship, rocket ship. And you just look around and you don't see this falling because that's not the only thing gravity does. Gravity can give rise to different results depending on different arrangements. That's the upshot, okay? So when you look at the pictures of satellites, you see like, or like not only satellites, but also like these space stations, right? There's like a space station here, and there's like an astronaut. And you look at the astronaut and say that, okay, here's the astronaut, here's the space station, here's the Earth. Why is this guy not falling on Earth? He's floating in the air. And you say, he's actually weightless, or she is actually weightless. My point is, he or she is not weightless. He has weight, and there is still gravitational pull. It's the same pull you here see for the apple, but the result of this pull is completely different. It's not falling, but it is actually circular motion. So my message is this one and this one are not so different. You feel the weight as much as you feel the weight here. So a geosynchronous satellite is one that stays above the same point on Earth. Okay? It's always like, say, if you are above Ankara, you are always above Ankara. You just spin with Earth. And this is only possible, your book says, above a point on equator. And then there are some use for such satellites, blah, blah. So now we want to determine the height above the Earth's surface such a satellite must orbit. What is the height here, h, that this kind of motion is possible? So here's the one I copied from the book. So he's saying that F12 is like this. So for me, so if I were to fix the same way they do, okay, let me write in red and compare what I messed up. So this one here is 2, this one here is 1. R21 goes from 2 to 1. Okay. So R21 goes from 2 to 1, which means it's R2 minus R1, right? So R21 goes from 2 to 1. So this, maybe I can clean this whole thing. So R21 goes from 2 to 1. This is R21. This one is, then R12 goes from 1 to 2. R12 is equal to R1. Okay, I don't have enough space for that. R12 is equal to R1 minus R2. Now, okay, thank you for that. Thank you for not letting this go, slip away. Now, if I fix it, so this one doesn't matter, right? This one, R12, R21 is the same thing. So we need to fix this guy. And maybe I can also, just to agree with your book, just for agreement, it's the same thing, but this one doesn't matter. But here I want to put some unit vector here. So this is force on 1 by 2, force on 1 by 2. And it should be like this. And this is minus R21, right? So R21 is this guy, minus R21 is, yeah, right? It's like the force is along this direction. And it should be minus R21 unit height. Thank you. Let's go ahead and solve this problem. So you are like a height h above the Earth, and you rotate with the Earth, right? So what you have is, okay, let's first write the force. Force is equal, or yeah, it's always like F is equal to ma, right? Total force is equal to ma. Total force is gravitation. Okay, I don't like this color. So gravitation, okay, G m m divided by radius of Earth plus h square should be equal to what? Yes, centripetal force, right? Should be equal to m v squared over radius of orbit, which is r plus mv squared over r. So we can cancel these guys. And V is equal to, I need to write an expression for V. And we are, just to remind, trying to determine the height. And for this, V is, again, I think 2 pi r plus h divided by t. So let's pull this guy down. Oops. Just this part. This is V. Actually, I can also cancel these guys. I want to keep writing those. This is equal to 4 pi squared r plus h squared divided by t squared. Anything else to cancel? It seems like that. Now, r plus h cube is equal to, I have g m divided by 4 pi squared, and this one is, I think, t squared. Is that correct? Let's check. I have g, I have m, I have rh cubed, I have 4 pi squared, and I have t squared. I think I have everything. I didn't miss anything. Now I take cube root of each side, and I need to clean this one. And that's it, right? T is, I think we already calculated, it's like, T is 24 hours. So then H is equal to cube root of GMT squared over 4 pi squared minus radius of Earth. Let's calculate this. So H, let's call it satellite, is equal to cube root of something. I'll write it like 1/3. Sorry, 1/3. And inside this cube root, I have G times I have mass of Earth times I have T squared divided by 4 divided by pi squared. Right? And let's subtract the radius of Earth from this, like this. Is on the corner of the screen, okay? And H satellite is equal to. So this is in meters. I think that's a lot of digits. Let's write it like in kilometers, and I want to format this guy. Format in scientific notation. Like, let's do, I think it was something like this. 1.1 E, something like that. Okay. Maybe 1.2 E. Okay. So this is basically 3.59 times 10 to the 4 kilometers. It's actually 35, I think, around kilometers, okay? So your book wants you to compare this distance to radius of Earth, but I think it's also kind of, okay, I need to show you. Okay. So your book wants you to compare this result to the radius of Earth, but I think it's also abstract. So this distance, for example, you can compare to a flight from Turkey to, I don't know, maybe US. And to cover the same distance, you have to go back and forth at least twice, okay? That's how much it is for that satellite. That's how much go up you have to go up. So let's calculate the speed of the satellite. What is the speed? I think we already have the speed. And here V is equal to, okay, I think that's the speed. From here, we already have everything. So let's calculate that. So that's your password. That's V satellite is equal to 2 times pi times RE plus H satellite divided by T. And this is in meter per second, okay? So if you look at that, that's some crazy number, 3071 meter per second squared. 3073 meter per second square. If you want to calculate this in terms of like kilometer per hour, let's do that too. So this is meter per second. So now it is kilometer. Now it is 3600 hour. It's like 11,000, right? 11,061 kilometer per hour. That's an extreme speed. Now, I think for the last one, you can probably compare the speed of satellite orbiting 200 kilometers above Earth. That's for your exercise. What if mg wasn't equal to mv squared in a satellite in the question? So if mg was not equal to mv squared over r, there were two scenarios, right? What if v is bigger than this equation? What if v is bigger? If your mv squared over this is bigger than mg, actually, maybe I can look at here. Is mv, if v is bigger such that this whole thing is bigger than this, so your satellite is going to fly away, right? It's just like, since it's like too fast to be pulled by Earth, it's going to fly away and it's just going to go to deep space. That's one scenario. If V is smaller, such that this whole quantity is smaller than this, then your satellite will fall on Earth. And that will be a catastrophe. Wonderful. So I want to talk about this weightlessness a little bit more, and let's consider this toy experiment. Okay, imagine you are in an elevator, and imagine there's like a scale from the elevator, like this. And on this scale, there is some mass hanging. So you can look at the reading, and you can decide the weight of this mass. Let's start with the simplest case. The elevator is at rest, or it could be moving with constant velocity. It's the same. So if this is the case, Newton's first law is like this, but net force on the weight should be zero because it is at rest. Then weight, the tension on the string, we call it W, which is the reading on the scale, minus mg should be zero. So W, the reading on the scale, is mg. So the second thing, now, so this was the elevator at rest. Now consider elevator is going up with some acceleration a, right? Now Newton's law, again, W is W, mg is mg, right? W minus mg. But this now should be equal to ma because this whole thing is going up with some a, right? From this, if you look at W, It's like usual mg plus some ma. And when you look at the scale and you say, okay, this same mass, but it is a little bit heavier. It will be a little heavier. Now let's substitute this A, like imagine it's going down now, and it is going down with G, right? I just substitute minus G here. So what will happen is basically this means this whole elevator is falling down along with everything inside. And if you put this and look, solve it for W, W is like minus mg plus mg0. And you look at the scale and you say, okay, this guy is weightless. So that is the weightless now, right? And if you release something you're holding, it's going to float in the air and you'll say, okay, I don't feel a weight, things are floating, there is no gravity. But what is actually happening is this whole thing is falling. So you still have the gravity, whether you see it or not, okay? Now let's come to the applications of Newton's laws. And the one direct application is orbits of the planets. And during Newton's time, I think there was like a lot of data on planets' motions. And Kepler is like a Dutch astronomer, if you like. He actually analyzed this data and he came up with so-called Kepler laws. Kepler actually has 3 laws, but I just want to focus his 3rd law today, okay? And for this, here's the arrangement. Basically, these planets, in actuality, they orbit in elliptical orbits. And elliptical orbits have 2 geometrical quantities. One is semi-major axis, this guy, S, and the other is semi-minor axis, B and B. So, and Kepler's law was this: for any given 2 planets, 1 and 2, their orbits T1 over T2 squared was proportional to their semi-major axis ratios, like cubed. Or you can rearrange this and say that T1 squared divided by S1 cubed for a given planet is same as T2 squared divided by S2 cubed for another planet. Okay? And Newton came up with his law of gravity, and he was like able to derive this result based on his theory of gravity and laws of motion. Okay. Here I want to focus on circular motion, so I will take B is equal to S equals to R to show Kepler's motion, and you can substitute here. Let's substitute R equal to S, or S is equal to R, like a perfect circle. And I want to derive Kepler's law for circular motion. So how can I show this? Okay. We need Newton's laws of motion with speeds maybe, right? Actually, we already did everything here. So let's just repeat this. So let's just repeat this and let's see if we can get this result. So we have the sun and planet interaction, which is, let's call it Gm m over r squared again. Maybe I can, yeah, I think that's okay. And this should be equal to the centripetal force of the planet, which is m planet v squared over r, right? And v, as usual, is always like 2 pi r divided by t. And I'm looking for an expression for, let's say, r cubed divided by t squared. I want to find this quantity. Let's manipulate this a little bit. Okay, let's cancel what can be canceled. M, r, which is good. I only have v squared. You can see. So from here, let's write this to V squared is equal to Gm over R. Okay. Then this one is equal to 4 pi squared R squared divided by T squared. So I already see this R can be taken to here and everything else can be taken to here, other side, right? Then R cubed divided by T squared is equal to Gm, right? Divided by 4 pi squared. So you can see for any given planet, so this is the mass of sun, and it only depends on mass of sun. So R cubed over T squared, whichever planet you take is this thing. So let's calculate this. For this, I need the mass of sun. Okay, mass ms, let's call this 1.989 yearly 30. This is kilogram mass of sun. Okay. Now we can come back. That's all I need. Then I don't know, Kepler constant, if you like. Kepler constant is equal to G, we already have G times m sun divided by 4 divided by pi squared. And let's see what it is. It's like 3, this is equal to, at least for solar system, this is 3.36 times 10 to the 18, right? And the unit is meter cubed divided by second square. So if you calculate this in, okay, I need to show you the screen. This is the result. This is meter cubed divided by second. And I think you should convert this to kilometer cubed by year squared. And you will see it's actually this table from your book, okay? And this is like observational. You can look at the distance from the sun. You can calculate year in units of Earth year, and you can look at the ratio. You can see this is pretty close to what we got. There's like Mercury. I think there's the biggest difference is Mercury. There's actually a reason for this. Venus, Earth, Mars, Jupiter, Saturn, they're all about 35, 36, right? I think which is remarkable. So maybe I can comment a little bit about, I think this is a remarkable result. It used to be a remarkable result at Newton's time, and it is a remarkable result in our time. So in Newton's time, there was actually deviations from this Kepler's law in Saturn. And Newton knew about this deviation. And he actually calculated these deviations by taking into account presence of other planets. Basically, any planet also affects other planets. It's not just one sun in the center and one planet. If there's something else, it should also affect the perturbation. It should also perturb the orbit of other planet. Newton did this calculation, and he actually found perfect agreement with that perturbation of Saturn. And that was actually a good, convincing result for him to believe his laws of gravity was correct. Later in 1930s, there were like very sensitive measurements of this Uranus orbit and its period. And people also found significant deviation from Kepler. And they could not account these deviations with the known planets. And they said, okay, there must be another planet that causes these deviations. And they actually, when did the calculation and look at the outer space carefully, they discovered Neptune. In the same way, later Pluto was discovered. Okay. Another thing is these planets affect each other's orbit, but also they affect the orbit of Sun. The Sun's motion is also affected by planets' presence. And this is actually useful. If you are looking at outer space, like distant stars, for example, if you are looking at this Ursa Majoris star, people find some kind of wobbling effect. And from that wobbling effect, they see, okay, there must be a planet around this. That's why it's doing this like wobbling. Similarly, this Epsilon Andromeda, which is also a star in astronomy, it's found that it has also like planets like Jupiter, more or less. Okay. So, and also this is not only just planets and stars. Like, for example, a really hot research topic now is so-called dark matter. And presence of dark matter comes from anomalies of certain stars in the galaxies. So galaxies seem to have like spiral shapes. And if you look at the motion of these stars at the other outskirts of these galaxies, there seems to be some deviations from this Kepler's law, this kind of behavior, okay? So if you look at some planets, you find V, 1 over square root, there are like deviations from these in certain galaxies. And from that, people actually propose something called dark matter. And what is surprising is that like the universe seems to be composed of like mostly dark matter, and we actually cannot see it. Okay. So finally, I want to finish with a little bit more about this gravity. So in the Newton's time, it was a little bit uneasy to propose a force that was acting at a distance, okay? Because the more familiar force is the force that's in contact. So how can I affect you if I don't touch you, right? If you are at a safe distance, I can't do anything. And this was actually not an easy thing to swallow. And how can two objects separated spatially affect one another? So later in, I think, 19th century, study of electromagnetic forces resulted in a concept called field. And this same concept was later applied to gravity, and it goes like this. So whenever you have a massive object like Earth, it causes some fields like this, those field lines that we can't see, but they are physical reality, okay? And if you have like a smaller mass, it also has its own gravitational field. And through this mass attracts this mass, and or opposite way, right? This bigger mass is catched on the gravitational field of the smaller mass. So basically this action at a distance or force at a distance turns into a kind of contact force. And for this, we define this gravitational field as force on a unit mass, which is like G is equal to F divided by M. And to remind us this is like the gravitational field, we keep the unit Newton per kilogram squared. And in vector notation, you can just do this calculation we did. G is equal to unit mass, 1 over M, times the gravitational force. And this gravitational field turns out to be G M over R squared around Earth, for example. And in vector notation, it's attractive. That's why I put this minus here. It goes like this. So to finish, I want to make a couple of comments about this gravitational field. Now, in modern physics, we know other fields. There are a lot of fields, and every field comes with its force. Or you can think about forces, and there are actually a lot of forces in nature. Today, we are familiar with electric force and magnetic force. If you have ever studied like electricity and magnetism, you're probably familiar with charges and currents, and they have their own forces. In the nuclear physics, there are like strong and weak forces. These are also acting at a distance. So due to Einstein, electric and magnetic forces, today we know they are the same force. Relativity dictates that they are of the same origin. And there are also some suggestions that strong and weak force are of the same origin too. Now, finally, all of these forces, at least hypothetically, can be unified in a so-called grand unified theory. I think what is remarkable is today gravitation is the most unknown force in all of these forces. And it's a big puzzle how to reconcile gravitation with all these other forces, okay? So just because something is simple and we see it around and we can study it, doesn't mean it is like easy to understand. From now on, I want to solve one or two example problems. Show that if a satellite orbits very near the surface of a planet with period t, the density defined as mass per unit volume of the planet is given by this expression. Maybe I can draw a picture like this. You have a planet and there's a satellite. Let's say this satellite is very near the surface. We neglect this little. And its period of the satellite t. And I want to calculate from this t density rho. So what do I do? Maybe I can write what density is. Density is mass. Okay. Let me make this a little pretty. It just looks a little messy now. Density rho is equal to total mass divided by volume, and total mass is divided by volume is like, let's suppose it's like a perfect sphere. And I think this is that. So here, when I look at this, m is m, so there is not much I can do. But so I look at r and I say, okay, I don't know r, right? I want to express this r in terms of what is given. And what is given is period of the satellite. So express r in terms of t. So how do I do this? How do I express r in terms of t? I think we have only one trick, and we have to use this trick over and over again. It's like g m over r squared. This is Newtonian gravitational force is equal to m times a. A is circular motion v squared over r. Just clean this up. M r r. And v is equal to 2 pi r divided by t. And this is equal to 4 pi square r square divided by t squared. Then, okay, I look at this and I collect r here, r square here, I collect r cube. R cube is equal to Actually, I want to do this way. So I can take, just to do a little less calculation, I can take r to here. So that will be 4 pi square r cube is equal to gm t squared. So I can divide both sides by pi, and this guy, here you go. I can divide both sides with, oops, I don't like that color. Okay, 3, and this is already volume, right? Now I can substitute to here, and rho is equal to m divided by v is g m t squared over 3 pi. Clean this. This is equal to 3 pi over g t squared. So this whole thing was a. So now estimate the density of Earth given that a satellite needs surface orbits with a period of 85 minutes. Approximate the Earth as a uniform sphere. Okay, so let's just put the numbers. Okay, where is this? So T, okay, let's call this TS, T satellite is 85 minutes. 85 minutes means times 60 seconds. And I don't know, rho is equal to 3 times pi divided by g times ts squared. And this should be, let's calculate the unit. Okay, so the unit is 1 over, what is g? G is Newton meter square per kilogram squared. Newton meter squared per kilogram squared. And T is second squared. Newton is kilogram meter per second squared. So if I clean this up, clean this guy, so I have meter times meter squared meter cube. So this whole thing is kilogram per meter cube. Oops, you didn't see that, right? Okay. So basically maybe I can just write it one more time. But it's like, yeah, the unit works as it should. So this is the end of the lecture today. Thank you for coming.